Hi and welcome to the video lecture series on thin film flow modeling and simulation in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the first part of the second video lecture and it is devoted to the introduction and underlying theory. So here we have the list of recommended literature, of course the course compendium, and here chapter 5. And then there are some papers which I believe are of high importance. One of them is by our SHEAR professor Roland Larsson, and it gives the governing equations in EHL, which is sort of a generalization of the Reynolds equation that you will get acquainted to today or in this video lecture series. And then is an important contribution by Kees Venner on multi-level solutions of the EHL line and point contact problems. And this is a PhD thesis which has been frequently read by PhD students and master students that are looking into this field of modeling and simulation. The book by Hamrock could also be of interest. It has many interesting examples of the application of fluid film lubrication. Then there are a paper by myself and colleagues here at Luleå University of Technology, and it's on the cavitation in lubrication, which is also an own chapter in this video lecture series. Then we have another one which is strongly related, and it's one by a group at the Imperial College. This is the outline of the video lecture on thin film flow modeling and simulation, here in part 1 we're going to formulate the Navier-Stokes equations, and then in part 2 we will see what the thin film approximation is, and we will carry out scaling and dimensional analysis to obtain it, and what we obtain will actually be the lower dimensional model, more frequently referred to as the Reynolds equation, and that will be considered in part 3. In part 4 we will have a look at the film thickness equation, which involves a few interesting aspects. We will also take a look at compressibility, pressure density relationship, and then the pressure viscosity relationship, and then a little bit about the rheology, and in the end we will see a few example solutions. I'm sorry, I rushed it a little bit. Before the examples there will be non-dimensional formulation of the Reynolds equation also. So let's start, and we start by introducing you to the Cauchy stress tensor, because it is Navier-Stokes constitutive relation is really based on the assumption that this Cauchy stress tensor sigma is a function of rho, the density, T, the temperature, and the gradient of the velocity. And the gradient of the velocity is shown here as it is a matrix, because the velocity is a vector itself. And now this means that the stress acting on a fluid particle here in the figure down below is actually affected by these factors. So in the fluid particle element here, you see that it's affected by the v, the velocity. It has a velocity in some direction. It may be affected by an external force field, could be gravity, here denoted F. And then we not only have ρ and T, but there are also other material parameters, mu and lambda, as we will look into on the next slide. So the Navier-Stokes fluid model is obtained by assuming or requiring that the Cauchy stress meets a few requirements. One of them is isotropy, and this means that the fluid behaves in the same way in all directions. It also needs to meet the frame indifference requirement, and that is that the material, the rheological behavior of the material, which is a fluid in this case, is independent of rigid body motion. And independence of rigid body motion is also equivalent with independence of the choice of frame. So as long as the frame is rigid, it may be chosen freely. The third requirement or assumption is that the Cauchy stress is linear in the gradient of the velocity. And under these requirements, we obtain the classical compressible Navier-Stokes fluid model, which allows the material moduli to depend arbitrarily on density and temperature. So lambda and mu can depend on the density and the temperature as indicated by the functions here. And also the pressure may vary on these parameters. And P here is the thermodynamic pressure. We will later on see what is the definition of the mechanical pressure. But this is the thermodynamic pressure, and lambda and mu are the two viscosities that appear in Poisson's original development of this model. Finally, the last term which is involved in the Cauchy stress is the symmetric part of the velocity gradient. So if you take the gradient of V and you add the transpose of the gradient of V and then take half of it, you get this symmetric part of the velocity gradient, as you can see in the matrix also. It's very symmetric. So now the Cauchy equation, we talked about the Cauchy stress, and the Cauchy stress sigma is included in the Cauchy equation, which describes the balance of the linear momentum. And it reads precisely like this, when we have the density ρ multiplying the material derivative of the velocity on the left hand side, and then ρ times here g, which now is external body force. Rho g is external body force, and we have used g here to indicate that it is typically due to gravity. So that's the first term on the right hand side. And then the second term is the divergence of the internal body force. The divergence of the Cauchy stress tensor or matrix, which is the internal body force. And here we can see the explicit definition of this one. And the material derivative, you're probably familiar with that. It is both the partial derivative with respect to time and then the velocity part of it. So V, the divergence between V and the nabla operator. So if we insert the expression for the Cauchy stress for the Navier-Stokes fluid model into the Cauchy equation, we obtain the classical compressible Navier-Stokes equations, and they may be formulated in matrix vector form like this. So nothing more than taking the Cauchy equation for the balance of the linear momentum and inserting the expression for the Cauchy stress for a Navier-Stokes fluid model of a compressible fluid. So of course we can express this in 3D Cartesian coordinates, component form, and we have x, y, z components listed here, and then the balance of the linear momentum looks exactly like this. The classical compressible Navier-Stokes equations, as we now have had a quite deep look into, have 5 dependent variables, and those are the density ρ, the temperature T, and the 3 velocity components V, U, and W. Which means that we need 2 more equations to fully specify the system. We have 3 ones in the Navier-Stokes, but 2 more for the 5 dependent variables. And in addition to this, we need constitutive relations for P, lambda, and mu. One of these equations can be formulated for the conservation of mass, and it's expressed here. Now it states that the rate at which mass enters the system must equal the rate at which the mass leaves the system, plus any accumulation or loss of mass within it, if there is a sink or source. So the partial derivative of the density with respect to time, that term, it can be interpreted as the accumulation or loss of mass in the system, while the divergence of the product between the density and the velocity represents the difference in flow in versus flow out. This equation is often referred to as the mass continuity equation, or simply the continuity equation. In addition, one second equation is an equation for the conservation of energy, and it is given here. And here on the left hand side you have the product between the density and the material derivative of the enthalpy, the specific enthalpy. T is the temperature, and phi is a function which models the dissipation of viscous energy. Here, the governing equations for a compressible fluid flow are summarized. So we have first the classical compressible Navier-Stokes equations, and then the continuity equation, and then the conservation of energy. So with this, we have 5 equations for our 5 unknowns. Let us now consider an incompressible fluid. So when we have an incompressible Navier-Stokes fluid, the flow is isochoric, and we'll come back to this. And in this case, the continuity equation simplifies quite significantly, and it just becomes the divergence of the velocity being 0. So we note that if the fluid is incompressible, it has constant density. That's the meaning. And then we have a constitutive relationship between pressure and density. However, if the flow is isochoric, does not mean that it has constant density. So the converse is not true. If the fluid is incompressible, it has constant density and the flow is isochoric. But the flow is isochoric only means that the divergence of the velocity is 0, not necessarily that the density is constant. Because of this, because of that the divergence of the velocity is 0, the trace of the symmetric part of the velocity is also 0, as can be seen clearly here. The trace is just the sum of the diagonal components, and the sum of the diagonal components is exactly the divergence of the velocity, and the divergence of the velocity is 0 when the flow is isochoric. So the Cauchy stress also reduces and takes the form on the bottom line here. So we have only one material parameter, one viscosity parameter, mu, left in the equation. And moreover, the pressure and the viscosity is of course no longer dependent on the density. This means that when the fluid is incompressible, the trace of the Cauchy stress, sigma, just become minus 3 times the thermodynamic pressure. And we can express this thermodynamic pressure P of T as 1/3 of the trace of the Cauchy stress sigma. And in component form that would be exactly minus 1/3 times sigma xx, sigma yy, sigma zz. And this is known as the mechanical pressure. So when reading out this equation out loud, we would say that the mechanical pressure is the negative mean value of the normal stress, because that is the normal stress components. It's quite common that the Cauchy stress is actually formulated in terms of shear stress also. So here the first expression is the one that we have been dealing with now until now. And instead of having the last two terms, we can express them in terms of a shear stress tensor, and therefore this shear stress tensor must be exactly defined like this. So we have shear stresses on the non-diagonal components, and we have added to the diagonal components normal stresses. We have also added the pressure. And if we want to expand this into the material parameters, the two viscosities, it will be looking like this. And we note that the trace of the shear stress would be 0 if the fluid is incompressible. Remember, because if it's incompressible, we have the mechanical pressure defined as the negative 1/3 of the normal or mean value of the normal stresses.